All right, so it's a pretty interesting example here that we'll use something called linear programming. This is related to some of the graphs that we've learned about how to graph inequalities. So the idea behind linear programming is that you have some what are called constraints, and those are equations or inequalities that we'll come up with when we do this example. We graph those constraints. You're going to get usually a shape of some kind where you have to shade above or below. So let's suppose you graph something and you get kind of this triangle type shape. You don't have to get a triangle, you could get something else. Right, and let's say we end up like this red line right here, it says stuff that's less than the red line, so we'd be shading below. But this green line right here, let's say that one also is supposed to be less than, and let's say finally that this blue line, when we actually graph it, turns out to be anything greater than that. So you can see we end up getting this region, this shaded in region, which is called a feasible region. Okay, and then we have to find the coordinates. We have to find these, in this case, these three coordinates, and then take those and plug them into a function which will be given to us in order to answer the question. Okay, so this is an example. I hope I haven't made you too hungry to do this problem. If you have to step away and grab some cake, I will understand. But this is a problem based on a bakery, and it says it's taken from an Algebra 2 text. It says Jenny's Bakery makes yellow birthday cakes for $25 and makes strawberry cakes for $35. Although the cakes are the same size, yellow cakes take 2 hours to assemble and to decorate, while strawberry cakes require 3 hours. So this is kind of important when you think about it. If you're a business, notice that the yellow cakes, although they are cheaper to make, or sorry, they're cheaper to sell. Okay, so you're not going to make as much money when you sell a yellow cake. It also takes you less time to make them. So that means you have to be paying your bakers, your workers to be able to make these things. So you're not going to make as much money off the yellow cake, but you will also not have to pay as much money for labor. Okay, strawberry cakes sell for 35. They're more expensive. That means you're going to make more money from them, but they also require more time. So this is a very interesting question for business owners, whether you're a baker, whether you're any other business owner. You'd like to know, what should my strategy be to maximize the amount of revenue, the amount of profit that we're going to make in the end. All right, so we need to do three things. We need to write our constraints down. Okay, and then we need to, it says up here, let me go back for a second so we can see our steps. We need to graph the constraints, find the coordinates of the feasible region, and then we plug them into our function to find, in this case, the max value. We don't really care about the min because we want to maximize revenue. So let's start with our constraints. So we'll make two variables here. It doesn't really matter which we pick. We'll let y stand for yellow cakes, so number of yellow cakes. And I would draw that in the yellow color, but you wouldn't be able to see it against the white background. And then we'll let x stand for number of strawberry cakes. Okay, so yellow cakes and strawberry cakes. All right, so how do we do this? Well, the first constraint, this is a real life example, the first constraint is that y has to be greater than or equal to 0, and so does x. And why is that? Because remember, this is number of cakes. You can't make a negative number of cakes. Okay, so that this constraint should be obvious. Y, however many yellow cakes we make, however many strawberry cakes, we can make 0, we can make none of them at all, but we can't make less than 0. Okay, so I hope that part makes sense. Then our next constraint, okay, we have to keep in mind this hour constraint right here. It says the bakery has 450 hours of labor available. Let's say they have a certain number of employees. Let's say they have 10 employees or 11 employees, and they can work no more than 40 hours a week. Let's say, so that means you have about 450 hours to get this done. Let's say you're trying to cater a wedding or something. That's how this might come up. So our next constraint is the number of yellow cakes. How many hours will it take to make the yellow cakes? Will it take 2 hours times the number? So if I made 100 yellow cakes, it would take me 2 times 100. It would take me 200. If I made 1,000 yellow cakes, it would take me 2 times 1,000. If I make y yellow cakes, in other words, we don't know how many we're making, it's going to take me 2y hours. Okay, and then the strawberry cakes, that's going to take me 3s hours because I don't know how many strawberry cakes I'm making. I do know it'll take me 3 hours per strawberry cake though. And then we have 450 hours of labor available. So this number could equal 450 or it could be less than. Cannot go over 450 because we don't have that much available. So there are three constraints, and actually I shouldn't have used S there. We're using X for strawberry. Those are our three constraints. And then here's the last thing. Here's the function. This last thing, we're not going to graph it, but we will use it at the end of the problem to find the answer. Our function is going to be the revenue, okay, or the revenue in this case. We'll call that R for revenue. And R is going to be what? R is going to be $25 times the number of yellow cakes plus $35 times the number of strawberry cakes, okay? That's what, and actually usually the way they write this to indicate that both X and Y are involved in this is they would write this kind of like a function, R of X comma Y. But you don't have to worry so much about that. All right, so our first step was to graph the constraints. So now that we have our constraints, we'll sketch a graph. It doesn't have to be perfect sketch, and certainly when I'm drawing it's not going to be perfect because I'm not a great drawer, as I think I've mentioned before. So our first constraint, Y has to be greater than or equal to 0. Okay, so here, right down here is Y equals 0. So the graph is going to be just this red horizontal line right there. That's the graph of Y is greater than, and we won't worry about shading just yet. So we'll just say Y equals 0 is that red line. X has to be greater than or equal 0. Well, this green line that I'm drawing is right where, this vertical line, that's where X equals 0. Okay, so we will have our two lines right there. And then our third constraint, let's change this one here. Let's change that into slope-intercept form. So we could do that. Let me just write it down here. We can do that by subtracting 3x from both sides. So now we have 2y is less than or equal to negative 3x plus 450. And then we will divide both sides of this by 2. And when we do that, we get y is less than or equal to negative 3 halves x plus 450 over 2 is 225. So that is our line. That's going to have a y-intercept at 225. This does not have to be drawn to scale, so I'm just going to label that. There's our y-intercept, and it has a negative slope. It's going to go down 3 over 2, and I would like to know at what point is it going to hit this red line, because that's going to show us exactly what our region is. So when does that equal? What does that equal right here? Let me do a blue dot instead. What's the y value at that blue dot? Well, it's right on the y equals 0 line, so that's where y equals 0. So let's actually solve this. We'll set it equal to 0, and we'll solve it for x to see when that happens. So if you subtract 225 from both sides, that goes away, and this becomes negative 225. Okay, and actually from that point, what you'd have to do, negative 3 halves x, in order to solve for x, you have to multiply both sides by the reciprocal. Okay, because the opposite of multiplying by negative 3 halves is dividing by negative 3 halves, which is like multiplying by this number. So negative 225 times negative 2/3, the negatives will cancel. 3 goes into itself once, it goes into 225 75 times, and then 75 times 2 gives us 150. So this point right here, that is the point x equals 150, y equals 0. This point up here is the point x equals 0, y equals 225. Okay, so let's draw our line right there. And now remember, once we graph the constraints, which we just did, our next step is to actually shade in the proper regions. So y is greater than or equal to 0. Well, if I'm looking at the red line on our graph right here, where is y greater than or equal to 0? Is it in region A or region B? And the answer is it's in region A. So we're going to be somewhere above this line, but I don't want to shade too much yet because I have to take care of these other constraints. So I know I'm going to be shading somewhere up here. Okay. Next step is we need to look at x is greater than or equal to 0. So let's say this is region A, this is region B. Actually, let me use different letters. We just used A and B. We'll call it C and D. So my question for you is, where would you shade in region C or D if x is supposed to be greater than 0? Okay, and the answer is, well, notice these numbers along the axis I'm drawing, these are positive numbers here. These are numbers where x is greater than or equal to 0. So what I'm going to do is shade in region D, because region D shows us where that happens. Okay. All right, and then so we kind of know, it looks like we're going to be shading inside the triangle. Well, let's just double check with our last constraint. Our last constraint is right here. Okay, it says y is less than or equal to that brown line. Less than or equal to, is that going to be region E or region F, where it's less than? And the answer is region F. So we're going to be shading underneath that line, and based on those other two constraints, it looks like the only way that we can meet all of those conditions is if we shade in this triangular region that you see me shading in right here. All right, so that's our feasible region right there. So we actually have one coordinate here, one coordinate here. It's a triangle, so it's going to have three coordinates. What is that point right there, right at the origin? That's 0, 0. So we have 2 out of our 3 steps done. We were supposed to graph the constraints. We did that. We're supposed to find the coordinates, those 3 coordinates of the feasible region, and that means the region that we get when we actually graph these inequalities by shading them in. What is our final step? Our final step is to use this function. We haven't used it yet, and to plug in those 3 points, because we want to, remember, we're trying to find out what should we do to maximize our revenue here. So let me rewrite our equation right here. Our equation for revenue is this, our function I should say. It's r of x comma y equals 25, what was it, 25y, because that's the yellow cakes, plus 35x. How do we now find out the maximum or minimum? All we have to do is take those points, 0, 0, and 150, 0, and then finally 0 to 25. We have to take those and just plug them in for x and y. So let's do that right now and see what gives us our best value. So 0, 0 is easy to plug in. That's just going to be 0 plus 0, which is 0. So obviously we probably don't want to go with that. Although remember, the maximum and the minimum is just, these numbers don't necessarily represent the money that you're making. It's just they're relative to each other. So whatever numbers we get here don't necessarily mean anything. It just means we have to figure out which one is the biggest. So 25 times y right here is 0. So 25 times 0 plus 35 times x. So 35 times 150. And then we'll calculate that in just a sec. Okay, and then finally our last one right here is going to be 25 times y. This time y, again we're plugging into this equation up here. Y this time is 225, and then 35 times x, and x is 0, so 35 times 0. Alright, so let's do this. So what is 35 times 150? 150 is 5 times 30, so 3 times this would be 1050. Is that 5,250, I believe. I'm just going to double check that in a sec with a calculator. But it's always good practice to try to do mental math if you can. So 25 is 5 times 5. 5 times that number is 1125. Times 5 again is, what is that, 5625, I believe. I'm going to double check this just to make sure we get it right. So 35 times 150 is 5250, that's right. And I'm just checking with the calculator right now. The other one is also right. So the question is, out of these 3 numbers, 0, that number, and that number, what's the best option? It's this one. That's the maximum number up here, which means when you're the baker and you're trying to figure out what should I do, this is what you should do right here. You should make 0 of these strawberry cakes, because X stood for strawberry, and you should make 225 of the yellow cakes, because remember, it takes 2 hours to make the yellow cakes. 225 times 2, that's going to give you your 450 hours of labor. Okay, and you might say, well, I thought the yellow cakes made less money. They do. Okay, but notice we ran it actually, and actually these numbers do give you the revenue in this case. Notice we ran it both ways, and if we made our 35 strawberries, we only ended up with $5,250. We made our 225 yellows, even though we're making less money for each of those yellow cakes. That's okay, because we were able to make more of them. We only made 150 strawberries. We made 225 yellows. So even though we charged less money, we ended up making more money, 5,625. So that's how linear programming works. You graph your constraints, you find the coordinates where you're supposed to kind of cut off that shape, and then you just plug them into your function. And it's very nice to know if you're a business owner or any other thing that's concerned with maximizing or minimizing something. You want to know how would that best be done. This is how you can do it.